So see, now continuing with the part, the image enhancement. So this is one of the key techniques. What is basically the key enhancement? Small briefs we basically introduced it yesterday. See that is basically happens at the two level. One level is at basically the spatial level. Another level is basically at the frequency domain level. As we discussed yesterday, see what is basically the frequency? What is basically the frequency here? Frequency here basically refers to the change in the intensity of the pixel. It is one of the very frequently used notion. So if there is a very quickly change in the intensity, then it is indicates high frequency. If there is a less variation, then it is the lower frequency. So initially we started basically on the spatial methods. The spatial methods when the things are directly working upon the pixel. So as we discussed it also yesterday, this what is happening that new pixel intensity is coming after applying the transformation. What is that transformation? It is some function, right? S equal to 2 r square, whatever may be the value, it can be here. So that the what happens at the gray level, output gray level of the output image that gets changed. This type of processing is known as point processing because the processing depends only on the gray level at that point. So what we are saying, because see here no more role of neighborhood is there. Whatever value, whatever output value of the pixel is coming, that is coming from the that input value only. So what we say, that is only the one value, so we say it is basically the point processing. So how does it act upon the whole image? It acts upon the whole image by taking the different operation on each pixel. What is saying here that when T operates on the neighborhood of fxy, what is fxy? Fxy is that pixel. Xy is basically the location. If you recall, fxy is that pixel value. The processing is done by the use of mask. Say 3 by 3 2D array. That is known as mask processing. What we are saying that see we take basically a 3 by 3. So here, for example, I am taking it here. So this is here 1, 2, 3, right? So it is the central point here, right? Or so what do we call this thing? We call this thing as basically the mask part, and this processing, it is basically the mask processing. How does it uh, how does it play a role here? Actually, when we are all these other 8 values apart from that pixel value, they also affect the final value of the output pixel. What has been saying here? Gxy equal to T fx of y. What we are saying that our this transformation, it is working directly upon that pixel value. Area or mass processing method. What we are saying, what is there? That input image is there, and then another part it is the enhance image. Here it is input image and input image is enhance. So why are we not able to draw the points? The point will basically vary with respect to the t. That what is basically the t? On that basis, there we will find a particular value. So regarding the point operations, operation deals with the pixel intensity values individual. The intensity value, so what we are saying that the, for example, we take that mask in such a way that the central value will coincide with that input pixel value where it has to work. The intensity values are altered using particular transformation techniques as per the requirements. What is the effect of that operation? That intensity value gets changed. The transformed output pixel value does not depend on any of the neighboring pixel value of the input image. Then whatever output you get basically, then it doesn't depend upon basically particular neighbor value. Example like the image negative. What happened in the image negative? Yesterday we basically saw the different type of example that basically when we are considering that it is L minus R. What is the another example that is basically the contrast stretching? What do you mean by contrast stretching? It means basically when we are some particular region is there and some contrast is there, we can enhance that effect of the contrast. Thresholding. What do you mean by thresholding? Thresholding means basically creating the boundary when you are creating the different boundary. Another is basically brightness enhancement. When we are saying here, see brightness, so for example, when we are stretching the contrast in the same way, for example, the brightness is limited to some region, it can be enhanced to the other region also. So yesterday actually we took up the many example of the image negative. Today we will discuss it how this thing actually work and we can see it in with the help of the example. So one thing is there basically that is the image negative. What happens in the image negative? That is basically that S equal to L minus 1 minus R. So L, what do we say? L is basically the total number of levels. For example, when we are taking the 8-bit, so it is basically the 256, right? Total number of 256 from 0 to 255 minus 1 minus R. So this is the so that's we are telling that how do we calculate the negative of an image. So it requires basically the initial pixel value and the maxima value. So and if you notice one thing that L minus 1 minus R here, that lesser the value of R, more the value of S will be there. That's why we also call it the image negative. It means the originally if some part was basically dark, it will become lighter, and the part which is lighter, that will become darker. So that is basically that it has been shown that reversing the intensity levels of an image in this manner produces the equivalent of photographic negative. This type of processing is particularly suited for enhancing the white or gray detail embedded in dark regions of an image, especially when the black areas are dominant inside. What has been emphasized here that whatever detail we want to emphasize upon, see for example, which is not originally visible in the actual image, then those regions can be basically contrasted. Those regions can be enhanced. So now coming to the part C, the another type of image enhancement operation, that is basically the general form of the log transformation. What do you mean by the general log transformation? See, what common thing you will note in these algorithms is that initial C fxy is there, it is operated in with some operation, and then finally we are able to get the output pixel value. What is that thing? It is basically gx of y equal to c log of 1 plus fx of y. What is c here? C here is basically 255 upon log 1 plus v max. can we infer anything about the exponential mapping? Yes, we can infer the thing that g x of y equal to c multiplied by k fxy minus 1. So this is basically the formula, and if we will go by the formula, so what we will get that c equal to 255 upon kv max minus 1, where c is a constant and it is assumed that fx of y is always greater than 0. Now coming to the part log transformation. So what is happening in the log transformation? The earlier we have seen basically the normal transformation. In the log transformation, the shape it has been shown here, it shows that this transformation maps a narrow range of low intensity values in the input into a wider range of output level. Something which is limited to very, very specific region and with a very low value. With that thing, we are able to basically get the wide range of output level. And this opposite is true for higher values of input level. We use the transformation of this type to expand the values of dark pixels in an image while compressing the higher level value. See, what will be the impact when you will take the log value? When you will take the log value, so it here, when it has been shown here that, for example, some identity is going on in inverse log, it is basically the log is there, that is nth root. This is so what we are saying here that negative line, it is basically coming here that the inverse log comes here and logarithmic basically nth root is on the this side. What is happening basically? Some see that the initial input intensity has been changed to a this output intensity level. So it is better to see with the help of the example that what is actually happening here. When we are taking this example of logarithmic and exponential gray level mapping, see for example, we can see the image of the car here, right? And we are seeing basically the another image of this related iPad device, which is open. If you really see the image, then it is not very easy to identify by seeing this. So what can be done here? So the thing which can be done here, that what we are seeing here, we are seeing basically the low value, right? Low value which is nearby the dark one. So what we need to do, if you see here, see the initial values has been basically changed here, and then after their continuous change, then it has been noticed that, oh, see what we have been doing here, that fxyc for any type of value, the value has been increasing in the logarithmic mapping. What do you mean the value has been increasing? It means basically the intensity of the pixels is shifted from the dark or less dark to basically color and colored. In the same way, there may be the areas where the exponential grayscale mapping can matter. So what has been shown here that when we move the value basically fxyc, it basically slowly varies, and when it will slowly varies, so when it is slowly what you are seeing here, see it has been slowly varying, and then you can see the other output value. You can see the enhancement of the image. See For example, it was there, already the enhanced values are there. So when we are you basically apply the gray mapping, it has become the this way. So is it better? Yes, it is better if you want to see the body part. That's why the designing becomes very crucial when we are doing the image processing operation. Now we can see basically the another diagram of basically power law transformation. See, what are the different transformation? The different transformation are the different values of the S. What is happening in the S? In S, basically, we are doing the single thing that we are enhancing the image. So first we need to know its function, that F equal to CR gamma gamma. So where C is basically the constant, and when you will basically draw this thing, when you are able to draw this output for the different value of gamma, you will able to get that type of curve which is basically given here. So it will basically slowly, gradually, it will increase. It has been increased, and when we are moving from the basically left to right. So we take another example of gamma transform. In gamma transform, see for example, original aerial image is given. Somebody has taken the image from a big height. Now the question arises. See, here a lot of things are there, but due to basically maybe it may be a sunny day where you are not able to observe the thing. What can be done? The thing which can be easily done here, that you do apply the gamma transform. What happens in gamma transform? It is the same function which you already taken, that C equal to 1 here, S equal to CR gamma. So this is shown here that this is basically the original is the aerial image, it is a transformed image. When you are taking the transformed image, can we see the change? What type of change is happening? So we can see here that in the original image, all the pixel intensities are concentrated into a small region. But in a transformed image, the things have been changed and they have been shifted from basically some narrow band to the wide band. That has been already said. So now coming to basically the after the transformation, the another transformation basically piecewise linear transformation. What you are doing in piecewise, definitely from the name itself, that piecewise will work out on the sum area only. So it is a spatial domain method. It is used for manipulation of an image so that result is more suitable than the original for a specific application. Again, see here, you need to go into the study, you need to go into the particular application if you really want to know the detail. Now coming to the different type of piecewise linear transformation, it is a contrast stretching, it is a gray level slicing, it is a bit plane slicing. So in the contrast stretching, what is happening here, that here it is basically contrast stretching transformation. Contrast stretching is a process. What is happening in contrast, as from the name itself, it reflects that it basically expands the range of intensity level. Slicing, where slicing, see, we will discuss in the last. Slicing, for the time being, you can understand slice. For example, yesterday we discussed that the value between R1 to R2, right? For some particular region, we are doing the transformation. So that is basically the slide, some specific part. Parvesh, is it understood? Even we will discuss into the detail. If you remember, we took up the example that where, yes, contrast stretching. Right? Contrast stretching is a process where the intensity range is expanded. Where the intensity range of intensity is expanded so that it spans the full intensity range. So what will happen if you would have really earlier seen that when the values were basically concentrated in a narrow zone, when it will be expanded into full zone, so it is far easy to see the every detail of the image. See the example. So that was basically the case of the contrast stretching and intensity level slicing. What is happening in the intensity level slicing? As we see, just discussed it, see that for example, some part is there. Some part is there where the input intensity has been changed in a small duration. Then see what will happen that in intensity level slicing in that particular part only, the transformation will occur. In which reason? What we are saying, see in this region. So one way is to basically to give the value of the 1 between R1 to R2 that it has been changed or the slice part has been changed. Another way that we can give one color. To that pixels having a range of intensity levels to highlight them and do not change the color of the remaining pixels. So there the value basically instead of 1 it is K and instead of 0 here it is R. If you remember in the yesterday lecture what we discussed that it is basically the base effect. One is basically taking into the base effect, another is without taking into the base effect. So here we are taking the base effect. Another example of the intensity level slicing to what we are seeing here that image is sliced to emphasize gray values from 150 to 200. So what has been shown here that see on the y-axis it is output value, on the x-axis it is basically the input pixel values. So between this region, the other region it is exactly the linear line. So it is a linear mapping. Whatever if it is 150 here, it is the 150 here. But between 150 to 200, the values has been changed. When values has been changed, we are able to see this type of image. That 150 to 200, it is there. So now continuing with the part intensity level slicing. So what is this picture basically consist of? This picture basically consists of the heart. In heart, what we are saying, see, for example, I want to highlight this. Highlight to blood vessel. What can be done here? So things which can be done here that they have basically made the contrast. If they have basically focused upon this region, other part they have darkened, and thereafter darkening, so the totally the image has been changed here. Now we will take up the example of contrast stretching. Contrast is basically contrast whatever we are discussing, we are all discussing basically the part of the transformation, right? In transformation, so when we directly see here, so in contrast starting, see basically three regions are there between here between R to A, and where R is less than B and then R is less than L minus 1. So in contrast staging, what we are doing, that S equal to L into R. In the between the A to B region, then it is basically S equal to M R minus of A plus B. What is this? This is basically again a linear line. And then thereafter, if we see the third level between the B and L minus 1, we can write that S equal to N R minus B plus W. Where what are this L, M and N? All these things are basically the slopes. So now we come to the part C. After covering basically the contrast stretching, and the intensity slicing. Now we come to the part bit plane. Intensity level slicing is basically limited to a small region. Bit plane is over a wide region. So what we are doing here, this is basically a technique which is used in image processing to analyze the individual bits in the pixel value. Here, each pixel is represented by a binary number. What we are doing here, that you analyze the individual bits in the pixel value. So how do you do it? Where pixels are represented by binary number. It commonly used basically 8 bits for grayscale images or 24 bits for color image. Why basically 24? Because it will become again RGB. RGB, so it is basically the 3 times. What we are doing here, that process of bit plane slicing involves separating and displaying each bit of the pixel value as a separate image. Creates a set of binary image where each one basically correspond to a single bit of the original pixel value, right? Most significant bit is basically the leftmost bit representing the highest order bit. The least significant bit is the rightmost bit, that is represent the basically the lower order bit. It has been shown here that in this diagram. So what we are saying, this basically the bit plane slicing. In bit plane slicing, we are saying that we separate the digital image into its bit planes. Remember, now the main focus word is basically the plane here. Earlier, like the intensity values. That is useful for analyzing the relative importance played by each bit of the image. So whatever your bits are there, we are able to see the role of it. So bit plane slicing can be used to the enhance images. For example, focusing on lower bit planes can reduce noise, while higher planes can emphasize detail. It can also be used for compression because we can allocate more bits to important planes, saving spaces while keeping vital image features intact. Bit plane analysis is an important tool for working with images. So what we are saying here, that when we are using for compression, so what we will take basically the MSB only. So it will give almost the approximately the same image. What happens when we are taking the MSB without taking basically the middle bit and the LSB, so it basically helps to reduce the size of the image. The image below to illustrate the process of bit plane alignment. What is happening here? We put is here that this is basically the image. This is how many rows are there. There are basically 5 rows are there, and it is a 5 by 5 rows. So how many pixels are there? Just 25. But when we are saying that, how do you want to illustrate the process of bit plane slicing? See, bit plane slicing, see all, what is the role? The question asked is basically what is the role of the bit plane slicing? See, the role of all these things, if you see in the earlier images, see for example here, when you are saying that I want to basically put a more contrast here, focusing higher plane emphasize the details. We actually see what happened that intensity level, some values have been changed, right? And at the plane level, large number of values have been changed. We will, let's see the example so you will get to know the detail here. So whenever you use this type of, whenever you will see this type of example, so first thing that this is the pixel value, that how many bits are required to represent it. So we will use the bits, for example, so higher it is the highest value, it is basically the 6. When it is the highest value 6, so we will, it is the 2 raised to the power, so it is nearby number is 8 and 3 bits are sufficient because 2 raised to the power 3 equal to 8. So what we will do, we will represent all these this matrix in form of the number, in the form of the binary number. Here we have shown it. In bit plane extraction, the number of planes, so how many number of planes, that will equal the number of bits. For example, 3 bits are there, so it is basically the 3 planes. Each bit is assigned to a separate plane. The MSP is assigned to the first bit plane and the LSB to the last bit plane. Now what you will do, then you will create basically the separate image for each extracted bit plane. Right? So what we are doing, plane is what I am saying, plane is, see, plane is basically of the 2 dimension. Plane is of the 2 dimension. When you are seeing here, for example, now we see it. See, what we are doing here, you are taking the first bit only. That 0 here. Let me, see, you can see here. See, this is basically 0 here. This is another 0, 1, 0, 1. So 0, 0, 1, 0, 1. You are taking the here most significant, so significant bit. So here you are taking, in this column here you are taking the again the MSB only, 1, 1, 0, 0, 1. Are you able to follow? First plane with MSB. Then you are taking the last plane with LSB. This is 1 here, so this is 1 here, this is 1 here, this is 0 here, and here we are taking again it is 1, and here again it is 1 here. So what we are doing basically, when we are, it is 5 by 5. So in the first plane we are taking the first bit or the MSB, and then the basically middle one we are taking in this one. That's why it is 1, 0, 0, 1, 0. And in the last one we are taking the LSB. Right? So this has been created. So this is basically a creation of the 3-bit plane. Now see what will we do? See, respect to bit, it means all will have the different intensity value. See that we will see. Still, we need to conclude it that what will happen after creating the different plane. This picture actually will better demonstrate you. For example, this complete picture is there. See this basically it is the currency of dollar, right? So when the currency of dollar, so what we are, this is basically of the size, as we already seen in our yesterday's class, that we take basically size in the form of the pixel. So it is basically 500 by 1192 pixels. So in B part, what they have shown, they have taken basically bit plane. They have taken the different type of bit planes there. So initially, when they have, so this is basically the so here now you can see here, see in this part bit plane one here they have taken it. Then this is the second one. Then this is the third one, fourth one, fifth one. So what they have done, they have taken the different plane and see what we are able to observe here that this figure, even see this is made up of the one bit only, but it is very much similar to the original image. So as we have been already noticing that what would happen, what would be the actual output when you will take the single bit. But when you have taken the single bit, you can notice here that this image, which is basically in the right at the bottom and at the right, see it is much more similar to the original one. What is this image? This is basically the most significant bit. Are you able to notice it? Many times, definitely, some combination doesn't work here, but in some combination, it is very good. We take them another example where the things will be much more good. So what we are saying here, when we are taking basically the original image, this is the original image. We are taken the three different original images. Now, again, we are taking basically the bit. What is the advantage? It can be done with log and forward down. See, advantage is basically if you see when we are using only one bit, it is basically the compression. When you are noticing all the information with single bit, so while as we have already yesterday we noticed it, you need to transmit only one bit instead of three bits, and it will help us to uh, compress the image as well as help in the communication. When your image is so it is overall it is a compression. In the same way, what you can notice here in this image where you are taking basically the bit, different type of bits, and what we are able to notice that even with a single bit, your image is much more similar. Yes, computational complexity is definitely there. But main advantage basically is the compression. Its size is very less. Here what you can see, so what is important, see in the image part, that whenever you are doing any operation, you are able to notice same type of change in all the images. So, see, such a you say what a wonderful invention of the bit plane slicing. It's simply using the one bit plane, it can reduce the basically size of the bits required, and it is almost giving the, it depends upon that how much precision you require the image, but for the 70-80% it is very fine. Is it clear? See, whenever you are going through the image processing, in the image processing, these mathematical things are very easy to see, check out. What we do, for example, any person has basically, they have basically developed their own mathematical thing. And when they are applying on the image, you are very easily able to check out the advantage and disadvantage. Don't need to basically, because what will be the impact in terms of the image? Because whatever impact we want to see, that we want to see in terms of the image only. that how is your image change, right? Now see one of the another important technique and very simplest technique. Should not rely that one of my friends see in engineering, he told me, where did you do the research? He told that see I followed the research because I know the one thing only, that histogram. What is histogram? Histogram basically, here you plot on the x-axis, it is basically different values are there, and on the y-axis it is the count, that how many these values are there. For example, here what you are seeing here, that 0 to 255, all these intensities are there, and how many pixels are of the 0 intensity, how many pixels are of the 50 intensity, that will be given by the y-axis. So can you believe? It's simple. This histogram processing has given wonderful results, amazing results in the image processing. Very simple mathematical operation, but how does it work? That we will see. So what is basically the histogram? As we just discussed, that histogram basically shows the frequency or the count. But an image histogram shows basically the frequency of pixel intensity value. In an image histogram, the x-axis shows the gray level intensity. So this is basically here, and the y-axis shows the frequency of these intensities. The x-axis of the histogram shows the range of pixel values. Since it's an 8-bit image, that means it is 256 levels of gray out shades. That's why the range of the axis starts from 0 to 255 with a gap of 50. Here we have taken basically the gap of 50. Where on the y-axis, it is basically the count of these intensities. So it is used in image processing. So we will see it. So what is its use? It's many use. So not only brightness, but are used in adjusting the contrast of an image. It is also to equalize an image. What do you mean by equalize an image? See, for example, some different pixel intensities are there, and if you want to equalize it. But remember, see, whatever operations are there, that which operation you need to do, it varies from image to image. It varies from your objective to objective. So now we start with basically, for example, first we see what is actually the histogram in terms of the image here, so that we can better understand it with respect to the image. For example, some image has been shown here. See, what is this? This is basically a one diagram where you are seeing the black values up to a some range, and then there in between the middle value, it is basically the gray value, and on the rightmost part, it is the white value. What has been shown here? What does it reflect? It is, see, how does basically the machine interpret this image? Machine will interpret this image in form of the matrix. What matrix? It will observe the matrix that it is 0, 0, 0. What is this matrix? This is 127, 127, 127. What about this image? This is a third subpart, that is totally the white here. So this is basically the 255, right? So that has been shown. This is basically the 4, 3, 7. This is basically the 10. So how many total pixels are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11 by 10 pixels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what has been, it is basically something. So intensity on the first initial, it has shown that the intensity, that these are the values of the intensity. It has been between the region. For example, it is it's a column here between 0 to 3 column, 3 to 6 column, 6 to 9 column. So what has been shown here, that between 0 to 3, it is basically the 0 value intensity. Between 3 to 6, it is basically the gray value 127, and between 6 to 9 it is basically the 255. The in between line which has been joining, so it is basically the boundary line here, right? So at the, what about the gray level histogram? When we will draw the gray level histogram, so what has been shown here, that the zero value, this is the 40 value, so you can count it, these four value, and this is these 10 rows are there, so this is 40. 127 values, so how many counts are there overall in an image? So that is basically the 30. How many values are in the 255? That is basically the 30. So what we are doing, we are basically analyzing in terms of the intensity value, pixel intensity value. Now we want to see the impact of the histogram. So now we are able to draw the histogram. Now we want to see the histogram processing. And we want to know that where does it work and how does it work. So for example, this is basically the figure of the some nuts, right? So what we can do, we can basically plot the histogram for it. When we have drawn the histogram, so what has happened when I have drawn the histogram, as we can see that the most of the values are in the black region or in the nearby of the black value. So when we will draw it, so we will able to get these values that you are able to see here. In the same way, when I have increased the brightness, what do you mean by increase the brightness? Increase the brightness means you have basically added the some pixel value, added the pixel value, or you have taken the negative also. That also we can say. If you take the negative, so what will happen? Whatever part it is there, it is on the leftmost part, it will reflect it towards the rightmost part. Why? Because if you remember, it is the capital L minus R. For example, the R value is basically 50, right? And it is L value is 255. So 255 minus 5 equal to 205. So it will come to the this reason, right side reason. So when we will draw the histogram of the bright image, it will look like in this manner. What about the low contrast image? What do you know the low contrast image? Low contrast image, again see, here we are applying basically the some slicing operation. What about the high contrast image? The high contrast image, see, it has worked upon, here it is basically the distribution. Distribution of the different pixel intensities, and it has been moved from the one domain, one part to the completely to the complete domain. So what is happening now with the help of the high contrast image, you are able to see the details of the nuts which were not easily visible in the original picture. In the same way, see what in histogram processing, again see the dark image is there. Uh, see dark image, what you can see. We can draw the histogram. When we draw the histogram, see what we are able to observe that darkness region is basically limited to the very limited one. What about the bright image? Bright image, as we already said it, that you need to take the negative, and when you will take the negative, it will come on the this side. What about the see high contrast image? High contrast image, see here, if you see here, the much more detail available here. You are able to see the trace of this baby. What type of dress, what type of colored strips, how many strips are there, that you are able to notice. Again, seen the basically low contrast image, the major issue. What is coming? That it is again limited to the narrow band, and we are not able to notice the minute detail. So this is basically it. And what about the histogram sliding? Histogram sliding means basically we are shifted it. Complete histogram shape, it has not been changed and it has been shifted. So what does it reflect? It is basically the brightness. What we say? In histogram sliding, we just simply shift a complete histogram rightwards or leftward, depending upon whether you want the darkness in the, whether you want to reduce the darkness or increase the darkness. Due to shifting or sliding of histogram towards right or left, a clear change can be seen in the image. So here, when we see sliding histograms, so this is basically one of the image here. So when if we add the 50 intensity to the each pixel, so what would happen? Everything, see, the detail of the picture has not changed, but it has been much more bright. So what is the change in terms of the histogram that you can see? That histogram of this image is shown here, and the histogram of this transformed image is shown. That is basically the slide. This is the old image here. This is the new image here. Another thing, see, there is basically the histogram stretching. What do you mean by the histogram stretching? Histogram stretching, say, again from the word itself, you can carry out. See, here we are basically stretching that part. Earlier, we have basically slide it, right? Stretching process that expands the range of intensity levels so that it spans the full intensity range of the display device. So from which range to which range? It is R minimum is the minimum intensity level and R max is the maximum intensity level. So what we are saying that the contrast stretching is obtained by putting this value where R1 and S1 are given in this way. So what we are saying, transformation function has been shown in this way. What is that thing? Really the transformed one. Another example, what you can see here, see this is one of the images there when you have basically applied the histogram stretching. Histogram stretching means that all the intensity values are lying. Here the intensity value between 0 to this one and the present higher value to 255 are not present, but when we basically stretched it, then what happened? Then in that case, the quality of image has been improved a lot. Another example, see where histogram stretching is applied. So there is basically the chest X-ray. In chest X-ray, if you see that the originally all the pixel intensity values were limited to region around 100, preferably between the 90 to the 120 on. So what is the way? See, when we see what we want to see that what is happening at this lung level. So when we are stretched it, so what happened that we are able to see many things. That we are able to see many things here, and again see there is no difference. That is all the histogram plots are basically from the different pixel intensity value, that is 0 to 250. So thereafter we will read basically the histogram equalization and what happens in basically histogram equalization. In histogram equalization is basically used to enhance the contrast. So here also that the gray values are basically uniformly distributed in 0 to 1. So what will happen in that case? In that case, basically the images, the quality of image will be enhanced with increase in the dynamic range of pixel width. So has been seen here that initially we are seeing this diagram, we are seeing this diagram in the first image, then in the second image. So when we are stretching the histogram, sometimes it doesn't work, but when we see the equalization, see what do you observe that this is that all the values are not only they are widespread, but they are also equal in size. That's why we say that the histogram equalization, it has enhanced the contrast. So I think here it is better that we can take one break so that you can. So this is histogram is one of the very famous topic where people used to do the lot of research in image processing without knowing the much. Come after 5 minutes, 4 4 around 4:10, 12 we will 4:12 we will start. I hope see. Now see what we are observing. That see in the histogram equalization and histogram stretching both look same, but they have one major fundamental difference. What is that difference? You see this basically the input image. What is this input image? In this input image, see what we are seeing here that the we say that the in between values of around basically 100 to 150, they are the present here. So one process is there that when we are stretching. So when we are doing the histogram stretching, so what is the impact here? The impact we are seeing basically in this, right? When we are doing the histogram equalization, in equalization, see what you can observe that not only we have stretched it, but also it has it has become flattened, right? So here in this part, in this stretching part, it is basically the basic shape is preserved. But in the histogram equalization, the basic shape is not preserved. And what is there that it is basically uniform distribution. That is basically the mainstay. That here it is the linear one, the shape is preserved, but here shape is not preserved. That we are seeing. Which one is better? That again we can always verify from the image, because see, there is no any mathematical formula that where you can say that this will work upon this will work better than another one. It is all about the image, that where does the actual pixel value lie there, and what we are seeing here that here it is a much more better, more information is available. What is happening basically in the histogram equalization at the mathematical level, we can see it here. For example, we have taken the original image here. So where the intensity is basically represented by the 3 bits 0 to 8 here. So that's why we have written at the gray level that from the 0 to 7, the value of 4 is basically a 14. We are doing the count here, and the value of the 3 it is 6, and the 5 is 5 1. So what we have done, we have basically plotted the histogram, and when we have plotted the histograms, we are able to see this that 3, 4, 5 values are there, other values are not present, and we are able to see the count. Now we want to check out that what would happen that when we will apply that process. Which one? Histogram equalization. So how do we apply the histogram equalization? See, first you see, again we take up the gray levels between 0 to the 7. We take the number of pixels. We have taken the number of pixels here. So one is we have written in the same order 0, 0, 6, 14, 5, 0, 0. Then what we have done when we have taken basically the PDF. What do you mean the PDF? PDF is basically we are total number of pixel upon sum. So we have taken it is 0 upon 25, is 0 upon 25, 0 upon 25, 6 upon 25, 14 upon 25. So then we have calculated this PDF. Thereafter, what we are saying, this is 0, 0. Now 0.24. Now what we will do, this 0.24 will come here. Now we will add up. It will become cumulative. Earlier it was probability distribution function. Now it has become cumulative distribution function. In cumulative, the final value will be add up to the 1. That's why we are adding it. I hope so you would have read it in the context of the communication, etc. courses. 0.24, it is 0.56, it is so 0.24 plus 0.56, it is 0.8, 0.8 plus 0.2, it is 1. And thereafter, 1, 0, it is 1, 1, 0, it is 1. Now what will we do with these values? We will basically multiply these values with 7. What is 7? Basically 7 is the maximum gray level. So that we have multiplied here. What we are getting value. This is the 1.24, 1.68 and this. Now the histogram equalization level. Remember the equalization level will be given by this one. We have taken 0, 0. We have taken 1.68 to the nearest level. It has become 2, 5.6, it has become 6, 7 will become already 7, 7. So that's how we have changed the value of the histogram 0 to 0. So 1 here also it is 1 also to 0, but 4 has basically changed to the 6. After equalization, how does it look like? Only these values are there 3, 4, 5. What you can notice, what are these values 3, 4, 5? 3 has become changed to 2, 4 has changed to 6, and another 7. So that we are basically able to observe in the output image. So this is the output image, gray level. So we can again see the histogram, or we can have the number of the counts of the different pixel intensity. In another example of the histogram equalization, the original image is shown and its histogram, it is already been seeing it. So again, we will apply the formula, and what we will get with the histogram equalization, we are able to get basically the high contrast image. Here we are in this image, you are able to notice the finer details on the nut, but here it was not clearly visible. What we are saying that the histogram equalization, but remember, as we already said it, that it may not always produce desirable results, particularly if the given histogram is very narrow. It can produce the false edges and regions. It can also increase image graininess and patching. For example, these points were given, right? And these points were given. So when we are plotting the different pixel intensity values or their histogram, it is limited to only very small region between almost basically 230 to 240 only, if you observe. So we want to check out that what would happen when we will apply the. Then we are applying basically the histogram equalization. See, again using the this our calculating the PDF and the CDF and then the SK, and thereafter we have calculated the next output value. In this output value, so when we have treated this operation, it has basically come out into this. And what is its image? Corresponding image that is shown. Now in the earlier image where we increase the brightness, here we taken the old image, old histogram, and here also we have applied the histogram equalization. After applying the histogram equalization, see, if you notice, see, in terms of the details, not many things are available. Even it is very difficult to say that whether is it really improved or not. So what are the basically the problems in the histogram equalization? The problems in the histogram equalization is basically that the image impurities are magnified. So that has been shown here. So what do we do to address these problems? We basically follow the adaptive histogram equalization. What do you mean by adaptive histogram equalization? That is in the image enhancement technique where contrast is improved locally. Adaptive. Where instead of applying a single global histogram equalization, you apply the things on a local region. What do? Here you basically divide the image into small tiles, then you perform the histogram equalization in each tile. For example, there the tile has been created. Tile or basically the block, what you are saying. So in the adaptive, so what we are seeing here, when the low contrast image is given when we do the histogram equalization, and when we do the apply the adaptive equalization, it is much more better. So the clip limited adaptive histogram equalization and the problems in adaptive histogram equalization, it can over amplify noise and low contrast area. Small tiles can cause excessive contrast and produce unnatural results. The image can look too sharp, too bright, dark. Patches, when each tile is processed independently, the differences between tiles may cause visible block boundaries, sudden intensity jumps. Another is there that you basically clip the of the histogram. What has been shown here, see, for example, some image is there with the original histogram and the gray level values. What it's suggested here that if we can cut, if we can clip here pixels which are above the specified contrast limit before applying the histogram equalizer. What do we call this thing? We call this basically the clay output. Again, see if you notice here that in this figure, the better visibility is there. In the original image, what you can see here, whether it is, has been changed. So here again, we have applied the clay processed image and it has been changed. So we have taken the basically the example, mathematical example that how does basically the things look like in this example. So here see for example, 8 possible values are there. With 8 level is there on the y-axis, this count is there. So when we are counting it basically, so it has been plotted in this way. Again, see as we need to finally make the, need to first draw the PDF and then the CDF. So then we will use it. So here what you can observe here that these pixel values, the 8 possible values are given, and during this value, what we are absorbing. So we will this 8 value, what we have done again, see we have done the same thing that we have calculated the PDF and then the CDF and then we have multiplied it by the highest level and then we have shown in the new histogram form. Another three important technique is basically the histogram equalization. Histogram equalization that yields an image whose pixels are uniformly distributed among all gray levels. Right? Now, first time we are talking, see, basically earlier we had been talking where things were limited to some particular region, but now here the pixels are uniformly distributed among all gray levels. This is the result of this, but this is not always desirable. What happens? We want a transformation that yields an output image with a pre-specified histogram. So even can we put up the output in such a form that where histogram is fixed? This is basically called the histogram specification. In other words, transforming the intensity values so that the histogram's output image approximately matches the specified histogram. take up the example. So gray levels is there. Again, it is basically the 3 bits here. So 0, 1, 2, 3, 7. It is 8 there. And in the transform part, it is all has been shown here. So regarding the histogram matching, what you are doing here, again you calculate the PDF, then CDF, thereafter CDF, and CDF basically we have summed up these things and finally it has reached to the 1, and then we have multiplied it by the 7 value. Basically CDF, we have got this value, and when we have round off it, we are getting this one, and then the new NK. We are getting this, and we will see it here. So this 135, when what we are doing it, we are basically rounding out it, that less than 0.5, it is considered as that number only. If it is more than 0.5, then we are rounding it to the next digit. So it is round off, after round off, it is 135 values given, then it is the 6 when it is there. So we will add up at 7 7. Again we will add up, and then and thereafter we will calculate the new NK value. What will be for any image? Is there any standard pixel size? So no, see, it is not necessary. Pixel size basically varies. Take from 100 by 100, then take from 500, 500. It is depends upon, see what really matters, that if you want the more resolution, then definitely you need the more number of pixels. When you are saying it basically now equalize histogram B, what we are doing it, we are continuing this thing. What we are continuing here. Now equalize histogram B. So when it has values are given, again, if we are capturing image from the same source, will it have the same pixel? Yes, see. Yes, basically we can say when you are taking the some device, so definitely. But see, yes, device wise we can say that it has that one capacity. Now equalizing histogram B, so when it is this value is given, that the number of count is given, and then its PDF is given. Then we are calculating the CDF, thereafter CDF, then we are again multiplying by the 7 part. We are 7 is basically the highest gray level value. Then again we are rounding off it, and after rounding off we are getting this value. So in the histogram matching, see what we have been saying here, that first and the last columns of histogram B, it is a gray level, it has been shown, and when we are rounding off, after rounding off, the new values are given. The values have been listed in this. So in histogram matching, see what we say, that the histogram of the input image is this one, and the histogram of output image, it has been shown when specified histogram is known. See, now the histogram is basically what are the things that which basically directly work upon the count value, the pixel count value. But till now, see, we are not actually focused upon the location. Where does your pixel lie? What is its neighborhood? Now, this is the turn to shift towards that with the spatial filtering. So what do we do in basically the spatial filtering? The first two words are there. Spatial means, again, it is for the image part, it is the two-dimensional, it is that plane on. And filtering means basically we are, if we have the option, we are able to filter out some information. or filter out some noise. So you have a choice to select the part of the image finally. So a spatial filtering technique is used directly on the pixels of an image. Whenever we are saying spatial, it works upon the pixels of an image. Mask is usually considered to be added in size so that it has a specific center pixel. This mask is moved on the image such that center of the mask covers basically all image. Spatial filter consists of basically neighborhood and a predefined operation. Now see the importance of neighborhood. You are seeing here two animals, that one is basically zebra and the Dalmatian. They have both have the black and white pixels in similar number. That is exactly the same. The difference, what is difference? This is the characteristic appearance of the small group of pixels rather than the individual pixels. This is the so in this spatial, so how does this thing take place in form of the image that we can see here? So what is this thing? This is basically the mask. Mask basically a size of the n by n. So how do we apply? You apply it in such a way that the 0, 0 element coincides with the pixel where you want to, which is the center one. So what do you do in this spatial filtering? Again, see you can see here that to denote the filter, X will for linear filtering. On the two type of the classifications are there on basis of linear. One is basically linear spatial filter, another non-linear spatial filter. So the regarding the linear spatial filter, it's basically satisfy additivity and homogeneity. It needs to satisfy all the constraint of the linearity, so the time invariant. Mean filter. Mean filter, what we are saying here, the linear spatial filter is simply the average of the. See what you mean by mean? Mean filter is also basically low processing filter. Here it is basically simply the average of the pixels contained in the neighborhood. What you do, the neighborhood effect actually comes there. It overall on the one node or the one pixel. Again, the idea is there, they're replacing the value of every pixel by the average of the gray levels in the neighborhood. Good way to on our averaging filter. It is used in basically reduction of the detail image. All coefficients are in. Now weighted averaging filter in this basically pixels are multiplied by different coefficients. Center pixel again it is put up there, it is multiplied by a higher value than an average filter. This way, once you have calculated the mean filter, then you can move towards the different type of mean filter. One is the averaging, and is the weighted average. So now coming to the parts, the correlation and convolution. Correlation and convolution. So how do they measure the correlation? When you basically directly multiply? Convolution basically not only you multiply, you basically flip the signal and you passes that signal through another one. You will see it here. So what is correlation? Correlation basically additive to homogeneity in Sobel filter. Gone through Sobel filter. We will go through it. See, we will exclusively deal with the Sobel filter. So better we will discuss it when we will go through these different filters, Sobel and median, Kenny. We will all go through it. So then we will see it. Correlation and convolution. Correlation, see what is basically what we are doing. In correlation is basically process of passing the mask. What do you mean by mask? Mask is basically again a 9 by 9 that window, or it is a, you can also say filter also. That is basically process of passing the mask by the image array. So what you will do, you basically put up the mask in such a way that every pixel of an image will become center pixel of that mask. It is often used in applications where we need to measure the similarity between images and parts of it. Now coming to the part convolution. In convolution, see how is it different? In convolution, one operation is extra that here you need to flip also before multiplication. So that has been shown here that the mask is first flipped. See, as we saw in our convolution, in the one-dimensional convolution, that when you convolve with basically x of tau with h of tau, first you do basically the h minus of tau. H minus of tau is a flipped version. Then you basically shift it and then you multiply. What has been shown here that if w x of y is symmetric, then w x of y equal to x minus y. That is the only difference between correlation and convolution. So what we are saying here, see 1D relation and 2D. So how we are able to see this relation? So in 1DC, for example, this here it has been shown here this correlation. That origin is there first, it has been shifted here. After shifting it, starting position alignment, so it has been, then we have done basically the, so what we are basically planning, can we cover it in the separate lecture on the our problem lecture, or should we cover in this one? What we will do, we will take up it in an example where we will deal with the mathematics. Only see what you can notice here. See what is this thing? Anyway, you just get to know. This is basically the see. For example, when we are doing it, so this is basically our mark 1, 2, 3, 2, 8, and this is our original. Basically, you say the image element. So what we are doing basically first thing that we are aligning the last element of the mask with the first element of the your original signal. Then what do you do? Then you do the basically the zero padding. What do you mean by zero padding? Zero padding basically add up the zero in that original segment. When we have add up the zeros there, so what is happening? So 4 zeros have been added. In the same way, 4 zeros have been added in the last, this example also. So then what do we do? Then we basically shift it. We shift the signal after the each shift, and then we calculate the value. So we have just shifted over the right, and then again we have shift. It is exactly the same thing. What we do in our original convolution of the one-dimensional signal. What will be the final position? The final position will be the one when the your 8, the last element will coincide with the 0. So what will be the this full correlation result? Full correlation result, if you observe, it will be 0, 0, 2, 8, 2, 3, 2. This has been shown. But when we are cropping it, so whatever be the value, what was the original value in the beginning, we will consider it as the same one. So it will be of the same length. So in the what is happening in the convolution basically flipped it. What do you mean by flipped it? There's the See, 1, 2, 3, 2, 8 was there now, but now it has become reversed. So can we really differentiate between the convolution and correlation apart from the flipping element? Yes, see, in convolution, uh, here the filtering and edge detection are there. The output gray level at pixel is weighted sum of the gray levels of pixels in the neighborhood. Kernel elements are taken left to right, top to bottom. Image elements are taken right to left and bottom to top. So it is used feature recognition, kernel, algorithm same. So now basically convolution and correlation are basically the operation which basically helps in the different type of spatial filter. What we are seeing here that the spatial filtering, that is smoothing, that is so one this for blurring and noise reduction, for example, that is called basically the smoothing. For example, that is again using a low pass filter. How does it work? The value of every pixel is replaced by the average of the gray level in the neighborhood. Type of smoothing filters are there. One is basically the standard average is there. Another is weighted average is there. Third is basically the median filter. So how you apply it, so that is as shown here, the cost multiplication in front of each of mask is equal to 1 divided by sum of the value. See, for example, somebody may say that when I'm applying it, I may need the normalized value. Like what was the actual impact of that algorithm on me? So here it has been shown that a constant multiplier in front of each mask equal to 1 divided by sum of the values. Values there it was 9 and here it should be 60. So in the same way when we will calculate it to the standard average, so it is 1 by 9, 1 by 16. So this is a standard average. So this is the standard average here when you have taken 1 by 9 and here you have taken the weighted average. And when you calculate the standard averaging filter, so what you will do, you will basically multiply all the elements to each value. To which mask it will apply? Again, it will apply where 94 is in the middle. You will apply it at the middle level. So 110 into 1, 120 into uh, this 1 plus 90 into 1 plus 91 into 1 plus 94 into 1 plus 98 into 2. What about the weighted averaging filter? Weighted averaging filter, it has been shown here that here you need to flip it up. So what you will flip here? See, when you will flip it, this is the original one, 1 to 1. When you flip it, it will this element. See what you will do? First, you will flip to this element and then to the this element. But you are what we are noticing here that the average value is almost coming. Filtering again, see what smoothing. Smoothing means basically rule out the noises. Rule out the noises in the surrounding. Where mask size determines the degree of smoothing and loss of detail. 3 by 3 images there, 5 by 7, 7 by 7. These images are there, 15 by 15, 20, or 5 by 25. And here, when we are applying the mean filter, see it has been. So, how does the smoothened image look like? Here, we have shown it on the image of the bird. that you can see here. Original image. On the left hand side, on the right hand side, there is a smoothing filter. Again, since we are using, and you can, for the different type of filter, for the 3 by 3, you will get this image. For the 5 by 5, get you this image. But normally, in our theory, in our practice, we normally use 3 by 3. So in spatial filtering, so what we are doing here, that this in input image, it is shown here that 11 by 11 kernel, that instead of taking 3 by 3, you are taking 11 by 11, and if you take 29 so what would happen? Definitely, when you are taking the more smaller one, it will able to better smooth. Take the bigger one, then definitely in one shot, it will not be easy to smooth. So now we coming to the non-linear filter. The non-linear filter, see, median filter is basically the non-linear filter. So how does the values are calculated? Basically, values are calculated where the median is the one. Median. The non-linear filter is basically based upon ordering the pixels contained in the image encompassed by the filter. It replaces the value of the central pixel with the value determined by the ranking result. How does the ranking basically matters here? So for example, as we have minimum filter, that 0th percentile filter is minimum filter, maximum 100th percentile maximum. So what we are doing here, see, when we need to find out the median, as from the name median, it is clear that first you need to arrange all the pixels in the ascending order. When you so when we will arrange it in the basically ascending order, then we will replace the original pixel value by the median. What is the median? Median is the middle element. 1, 2, 3, 4. This is two elements are there. 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. So this is the fifth one. Otherwise, if it is between the even value, then what we can do, we can take the average of these. So in the non-linear filter, it is basically used to remove the salt and pepper noise. Salt and pepper noise. So what do we do? Salt and pepper noise, basically it looks basically some white elements, some black elements are there. It has been very much used to justify the filter, justify the Gaussian filter. The same way it has been shown here. So for example, whatever the values are given of the set box where you are basically working, so you will order these values, and after order you will calculate the median. In another word, when you calculate the mean value, so what about the mean value? We are comparing in any type of our result both the mean and the median. So this is a diagram where non-linear filter, it is mean filtered and it is a median filter. So in the order statistic, it is so you would have been, I think, aware about the Python and the Python C. So if I want to apply the image processing on this brain slide, so it has been shown here. What we are doing, basically importing CV2 library. This is NumPy library. From CV2 image library, you are reading that image and then you are basically applying that function, and median blur is there. And then you compare it. After comparing, then concatenate it. So here we can see it here, basically here it is the chip part is there. In chip part, what you can see that the X-ray image, here salt and pepper noise is there. When you will do the noise reduction with 3 by 3 averaging, so when you are applying the median filter, when you are applying the averaging is basically the smooth filter. So there in the right hand side, when you can see here that median filter is providing much more better result when you are able to notice the many details. So what do you mean by the sharpening of the spatial filter? How can we make it further better? See, the aim is basically to emphasize the transitions in intensity. We also use Laplacian operator for it. We are basically using unsharp masking and high boost filtering. It is using first order derivative for basically nonlinear image sharpening, first order derivative that is given delta on fx plus on minus fx, and regarding the second order derivative, this is this. So in terms of the image, if you really want to see that, how does it look like that when we are taking this thin line and we are taking basically the flat segment. So when we are taking basically the sharpening the spatial filter in first derivative, basically the thick edge, in the second derivative, uh, we get basically the double edge. It enhances the fine detail. So it depends upon that whether we want to observe the boundary or whether we want to observe the even the fine detail. Fine details are basically part of the high frequency. Stop it. Lot of mathematics. So see what we plan that we will take up with more example these things so that you will better able to understand these things that what is going. Please open for your questions, whatever your questions are there. We have actually a little bit faster here so that we can take up the problems. We can take up the problems once we have gone through this content. Initially, see, we have covered basically the three things here, that the histogram, stretching, histogram equalization, and then the spatial filter. So it is open for your question. And so we conclude it here. Conclude it here with definitely opening out these things with a more problems so that we can better understand this part. Thank you.